this works, then hello and welcome back to this live stream of real analysis. Again, as last time, we will solve some problems in real analysis, and we chose the continuity problems here. Oh, no. I'm not alone. As last time, I'm here with Fabian. So, hello, Fabian.
Hello, everyone. Glad to be here.
So, how is your YouTube channel going?
So, last time I checked, some new subscribers were there. So we'll see where it goes from here.
Yeah, very good. Yeah, I hope you get some new subscribers because you have nice math content as well. So yeah, check that out. We do continuous functions. So I would say this is an important part of real analysis, and it's not too complicated if we just do it one-dimensional. So I brought problems that are one-dimensional, so functions from R to R. Fabian, you also brought problems?
Yes, and I also brought, hopefully some continuous functions from real valued functions on the real axis.
Yeah, we need continuous functions. And yeah, we will not talk about a lot of definitions, I think, because I have videos about the definitions and everything. This live stream is about solving the problems. And you already see there is one problem here. For the start, maybe we can recall some definitions there. But I don't think this should be a big problem, because continuity is something you have, you have an idea about. It's like there are no jumps. If you have an error in the input, it gives you an error in the output. So this is related. Something like that we will talk about. But here I would say we start with a simple function where we can use the definition with sequences. So the sequence definition of continuity. So hello in the chat. Maybe you can say that as well. If you have questions, if there are problems, while we are solving some problems, just tell us in the chat. You can participate there. And just write anything that's in your mind concerning the problems. Okay, Fabian, I would start solving this first problem. Or do you have any questions about that already? Maybe the audience also have these questions.
So I'm looking at the function that is defined piecewise, or in two sections, right? So it's we have one value if we plug in a rational number, and another one if we put something irrational in it. Not sure whether I can visualize this function, but so maybe
okay. If you can't visualize it, maybe we do that quickly.
Yeah.
So I have the graph of the function maybe. So we have x and we have 0. So okay, you know the graphs of these two functions. If there would not be this piecewise definition, but just the function x, you would know, okay, this is just the straight line through the origin that looks like this. It goes through the origin. Maybe I shifted a little bit. So this would be the function x, and the function 0 also is not complicated. Maybe I put it in here. So now the thing is, we mix that up with rational numbers. So if it's a rational number, it is on the blue line, and if it's not a rational number, an irrational number, it's on the red line. Yeah. So in other words, we have a lot of jumps. Yeah, because you know that the rational numbers lie densely inside the real numbers. So it's a dense subset. So it means no matter how much you zoom in, you always find infinitely many irrational and rational numbers. So therefore, we have a lot of jumps here in this plot. I will not visualize that because that's hard. But you can imagine, you can have one value there and one value there, and then if you zoom in, you always have this property. You always see a lot of jumps.
All right. So we have a lot of jumps, but if I read the problem text correctly, there's one point at which these jumps don't matter. So so jumps usually means the function is not continuous, but continuity is defined also for a point. So it's continuous at a point.
Indeed. that's good that you say that at the beginning. If we talk about continuity, it's always a pointwise property. Yeah, we can always say it's continuous at a given point. If we don't say that, then we mean, okay, it's continuous at all the points we are considering, but it's still a pointwise property. So it can fail at one point and it can be satisfied at another point. And here we want to show that it's satisfied at the origin. Because the picture says it's not satisfied in all the other points, but at the origin it's satisfied, and the picture also tells you that now, because you see this blue line and the red line both go to 0, so the jumps get smaller there, and there's no jump at 0. That's the overall idea here, and I can show you how it works. So, Fabian, do you know the definition with sequences for a function, for a continuity with sequences? Maybe
Yes.
I write it quickly down.
Yeah, so it means that if I plug in a convergent sequence of values in the domain of definition, so which would be the real line here. So if I have a sequence xn converging to x, all real numbers, then also the sequence of function values f of xn will converge to the value of f at the position x. So f of xn will converge to f of x.
Indeed. So we take one sequence with the property for all sequences that converge to this x0.
Yeah.
We have that the images f of xn also converge to a point. So it's also a convergent sequence, and the limit point, the limit is exactly f of x0. So this is for n to infinity here as well. Yeah, so not so complicated, but it says exactly what I said at the beginning. Yeah, if we go in the input space closer and closer to a point, then in the output space the same happens. Now this is continuity with sequences. A very natural definition, and something that helps a lot if they say, show it's continuous at a given point. Most of the time it's easy to show it with sequences. Maybe not all the time, but here it's the correct approach. Yeah, so x0 is now 0, and we have to choose a sequence. So to prove that, you would say, choose an arbitrary sequence xn, n in n, with the property that xn goes to, now it's 0. So now we have to show that f of xn goes to f of 0. Now the question is, what is f of 0 here? Maybe not a big question, but yeah, we see it here. If it's irrational, it's 0, and if it's rational, it's x. Yeah, so 0 is rational, so we have to put it here in the first case. Well, that gives us 0. So we want to show that f of xn now goes to 0. So how can we do that? Maybe we just write it down. So f of xn. Two cases. Either it's xn or it's 0, depending if xn lies in the rational numbers or if xn is an irrational number. So in Q, rational number or not a rational number. Okay, so now this convergence would mean f of xn minus f of x0 goes to 0. Measured in the absolute value, this is the distance. So now we can replace that immediately. We know this one is 0. So we just have the absolute value of f of xn. Okay, but on the left-hand side we already see this is either xn or 0. So this is definitely, no matter if it's rational or irrational, less or equal than x of n or xn in the absolute value. So on there we know this goes to 0 by definition, or by how we have chosen this sequence. So no problem at all. This goes to 0 if n goes to infinity. And there we have it. This means the left-hand side goes to 0, which means f of xn goes to f of x0. So we have exactly the continuity at the point x0, which is 0 here in the case. Yeah, so I can replace that with 0 here altogether, because this was the point we want to consider. Yeah, that's the whole proof. So not a real proof, it's just, here's an example. Check the definition of continuity at the point 0. And that's what we did now. Yeah, so I would say the approach is always the same. Just choose an arbitrary sequence that goes to the limit point you want, and then check what happens with the images. Yeah, and then write down the correct estimate to prove or disprove the fact there. Okay, I don't see questions. I don't see any questions in the chat about that. Fabian, do you have any questions?
No questions, but maybe a comment or to emphasize on one thing that you said earlier about the arbitrariness of the sequence that we need to plug it in. Because this is how continuity is defined, and we see it also nicely in the proof that you carried out. There is no choice of the sequence in terms of how it looks like. The only thing we know, it's a sequence and we know its limit. And it's nice to see that, it really plays a role here, because we cannot choose an example of a sequence that converges to 0 and then argue, okay, then it will be the same for all the other sequences, which may happen for functions that are not continuous at a point, that you still find a suitable sequence that fulfills this this relation or this implication that once a sequence converges, also this sequence of function values converges. But really note that we are working with an arbitrary sequence.
Indeed. Here. So this, in the definition, this all is important, yeah? So for every sequence you can choose with this property, you need to have that. It's not sufficient to just have one sequence, which would happen, as you said, if you just take a sequence. It's not enough. You have to prove it for all, which means for the whole proof, it has to be an arbitrary sequence. As you can't put any values for the sequence in. You just have to use this property. The property what the sequence does in the limit.
And we have one question in the chat on, I think, the last estimate that you have.
Yes. Yes, I said that quickly. That was just to writing it down in the correct way. Of course, you can have just two cases for xn. Either, and you see that here on the left-hand side, either it's xn if it's a rational number, or it's 0 if it's an irrational number. Because we have an arbitrary sequence, we don't know what xn is. It can be this case or this case. Therefore, I wrote it down as an estimate. In the worst case, it's xn. In the other case, it would be 0, which is also less than xn, because this is the absolute value of a real number. So it's always greater or equal than 0. So you can just write it down and it's always correct, no matter if xn is in the rational numbers or in the irrational numbers. And that was the whole thing. That makes the whole writing down of the two cases simpler. Yeah, but that's all. Yeah, you're welcome. Then, that's all for problem 1. So now we have some idea how we can prove continuity with a simple function, yeah, which looks complicated, but still can be continuous at a given point. So now, the second problem. The second problem is a problem from Fabian. So now I give you the pencil to write down the solution, which means we should change the screen. So in the meantime, you can already tell what is going on here.
Yeah, of course. So once again, we are given a real valued function here, but as a little twist to what we had before, this function depends on two additional parameters, a and b. And it also is defined in a piecewise manner. So we have, once again, this curly bracket that tells us, depending on the value of x that we plug in, our function will behave differently. So in particular, or more concretely, we have 3 cases to distinguish once we choose a value of x in which we want to evaluate our function. And I think it would be a good idea to make first a sketch of how the function looks like before we dive into the proof.
Yes, I would suggest that as well, to have a graph to have an idea how it looks, it's a good idea.
Yeah.
Because it's piecewisely defined again, but now with 3 cases. So yeah, I think a graph can help to see these 3 cases that can happen.
Yes. So I would say I see if I can still fit it in here. So you can see on the one hand the problem, and on the other hand the sketch that I'm doing. So I need to manage the space that I have left. So it's a function it's a real valued function. So first thing always to do is, so we make 2 lines. One is for x, the other one is for f of x. And then we work through the definition step by step. On the first part, let's focus on the right-hand side here to really know where we can draw each part of the function. So we have one case here in the first that tells us something about all the values of x that are less or equal than -2. Then in the second part, we are looking at all the values of x that lay between -2 and the value 4.
Mm-hmm.
And then we have everything that is right of 4, so all the x's that are greater or equal than 4. So now at each of these intervals, we have given a certain definition here. And so let's now take a look at the left-hand side of each case. So given the first case, we are looking at the function a polynomial x to the 4 minus 4. So it will be at -2. It should be something around 12. And then the function, so it does not fit so well on the screen, but so it will look like a parabola. So maybe steeper than the one that I just drew here.
Okay, but it's a curve that goes up.
Yeah, it's a curve that goes up to the left. We also know that it would continue something like this to the right.
Mm-hmm.
But we don't care about that here because we are looking at the function f.
No,
and f is only defined until the position -2 here.
You cut it at this middle point.
There's just a cut and then different story. So let's do 2 jumps ahead and look at the third case in our definition, which is a square root of x. So for x greater or equal than 4, our function is a square root. So if we plug in 4 here, then the square root of 4 is 2. And then the square root itself will look something like that. Yeah, so maybe it's too steep again. So square root will look something like this.
Mm-hmm.
So let me also maybe note some of the 2 values that we had here. I think on the left-hand side, we have -12. On the right-hand side, we have a 2. And now let's take a look at the function that is in the middle. And the idea now is, well, this is just a linear function. So you would draw it like a line in the plane. But it is parameterized. And we parameterize everything that you can parameterize about a linear function here. Mm-hmm. Namely, its intersection with the y-axis and its slope.
The slope is a. Yeah,
the slope is a. Yeah, and the intersection with the x-axis is b. And now, just to get a feel about what we are trying to achieve here is, so we want to be the function f, the f function, to be continuous on the whole real line. That means, intuitively speaking, it should not have any jumps. At no point there should be a jump. So how can we achieve that with a real function? That is
the real linear function.
With a linear function, how can we do that? Do you have an idea?
No, you already see the picture, so yeah. I would say there's only one, because you can connect the 2 points from the left and the right. So the red line and the green line have some endpoints, and you can connect them with a line. And I would say there's only one line that connects these, so you have a unique solution maybe for your values a and b, if you see the picture. And now it's about to calculate these values.
Correct. So now that we have a first sketch about what we want to do, let's now dive into the proof of continuity here. And it also consists of several parts because we see, first of all, the question asks us about continuity. Let me scroll up.
By the way,
About continuity on the
is that
whole
a
real
typical
life.
exam question as well?
Yeah, that could be an exam question.
Because I have seen some such exercises often in exams. So you have some parameters and you have to find the correct parameters to make the function either continuous or differentiable. So
yes,
a typical exam question, yeah.
It's a typical exam question, and the procedure that we go through is always it's also very similar each time. And so what we need to do is we once again need to segment this problem into subparts, because the question is about continuity on the whole real line. So there are infinitely many points, first of all, where we need to check continuity, and we need to reduce this down to a subset of points where we really need to calculate something, and another subset where we can maybe recycle some of the things that we already learned about continuous functions. So the thing about this the thing about this piecewise defined function is that it in fact consists of continuous functions. So if we take a close look at how we defined this, we can already state that f is continuous on the interval from -infinity to -2. Because on this open interval, the function is just x to the 4 minus 4, which is a continuous function because it's a polynomial. Further, we can do the same with the other two cases. So it's also continuous from -2 to 4.
Why?
Because no matter how I choose the parameters a and b, it will always be a linear function. Once again, a polynomial, and we know all polynomials are continuous. So I cannot find a choice for a and b for which the function ax plus b will not be continuous on this open interval from -2 to 4.
So at this point, you just have to state that you already know some continuous functions, and that this is not a problem here. So the problem is not that polynomials are continuous, because you know that. So you state the fact.
Yes. So nothing to prove here. But you need to recognize it and also make sure that you state it. So the drill is the same for the last portion. So it's also continuous on the open interval from 4 up to infinity.
Very good.
So we see where the problem really is to be located. Namely, it's located at these points here where we want to glue the functions together. Namely, at this point and at this point. Also note that even though the function definitions are defined on a closed interval, so as I'm talking about the function f and not the function that I have here in the definition, I first of all can only make a statement on the open interval, and I need to exclude the points where there may be a jump, because I'm jumping also between definitions. So we need to be careful with that. And well, stating it like this way, we have already reduced our problem to checking continuity at 2 points now. So to sum up, we need to check continuity.
Maybe I can tell you that. You checked continuity now for infinitely many points by writing down the fact that you know polynomials are continuous, the linear function is continuous, and the square root is continuous. So only 2 points remain, so just finitely many. So that was clear from the beginning, but still you have to say, continuous, or the continuity property is only a problem at these 2 points, really. So you just have to check these 2 points now. And these are the points where jumps could happen. That's what the definition already tells you, because there the definition changes.
So and now the twist of this exercise is not that we do a proof like we would do if we want to check for continuity, but we use it in a way so we like reverse the things that we do, because we want to determine the values a and b for which the function actually becomes continuous. So yeah, that's interesting, I think, and you should not be confused by that. It's by design that we carry out a proof like we would do for continuity, just to find the parameters a and b that make the function continuous. And then, of course, we have already a proof that shows us, okay, the function that we found will be continuous. But now let's do some calculations here. From the last part, from the problem 1, we already revisited the definition of continuity by means of sequences. And this is also what we're going to use here. So what we need to show at each of these jump points is that the limit for every sequence x going to -2 of f of x will be equal to the value f of -2. So this is the first thing that we need to prove.
This is exactly the definition of continuity, like I give it in the video course about real analysis and how you find it in a lot of books. Yeah, you define the limit process for functions, and then continuous at a given point means exactly that. The limit is the same as the value of the function at this point.
Yes. So that's what we need to check here. And once again, we can now recycle some of the things that we already know about the continuity here, because now we know we can use the fact that this that the function here is defined actually on the closed interval. So what this means is that we can divide the set of sequences that we look at here into those sequences that approach this possible jump point from the left, and those who approach this possible jump point from the right. And only one of these classes of sequences will be problematic, because we already know that this red function here is a continuous function. And it's a continuous function defined on a closed interval, so to say. So we already know that sequences coming from the left won't be a problem at all, because the function is continuous. And if I have a sequence that comes in from the left, then of course it will also the sequence of function values will converge to the function value at this jump point. So for checking the continuity of f at this point, we actually only need to consider sequences that approach this point from the right. And we do this by directly adapting what we need to show. So I don't need to write that much. So we are coming from the right. That means we use an arrow that goes from the bigger values to the smaller values.
Also what you usually define when you talk about real analysis, when you talk about functions or calculus, you define the limit from the right-hand side and the limit from the left-hand side. Yes. And then the whole limit is just both things together. And now you just need the right-hand side because the left-hand side is very clear.
Yeah, it's already continuous, so we do not need to check it again. So this is the thing that we need to check. And now if we take a look and we have sequences that converge from the right-hand side to -2, then we see at some point these sequences will be in the regime of x values between -2 and 4, which means this middle part of the definition takes place, which is why we can now substitute some values of f of x in here. And if x is small enough, then these values should correspond to ax plus b. But now, once again, we have here a continuous function. So we already know what the limit of this function here will be. So the expression that I wrote down here, well, it does not know any borders anymore. So that's what happens here now. So I can basically just plug in -2 here and get it as a result -2a plus b.
Not so
for this
complicated.
limit here. No, it's not complicated at all. It's I think what makes it complicated is all the stuff that you need to take into account in order to derive such a simple formula. Let's also take a look at the right-hand side here, because we still haven't evaluated f at -2. Well, we already did it while doing the sketch. So let's check again. -2 to the 4 is 16. 16 minus 4 is 12.
Maybe you can scroll up a little bit that we can see the function again.
Yeah, good point.
That's what you said now. X to the power 4 minus 4. You just have to put in -2 again.
Yes.
Yeah. Okay.
Yeah. So once again, an easy step. And so now, interesting fact, we are now reducing the problem of continuity to a problem of linear algebra, solving a linear system of equations.
Yes.
Yes.
We always do that here.
Yes. And this is just the first equation of our system of equations. And you can already guess from what we have done. We now need to do the same for this right spot here for x equals 4. And this will give us another equation that we then put into our system. So I think we can speed up things.
Yeah, I think
a little bit here.
You can write down the same equation.
Yes.
Now for the point 4 instead of -2. So
the only difference here will be now that we are interested in sequences that now come from the left. So we now are looking at the limit of x going to 4 from the left. Yeah, because when I come from the right, I already know the square root is continuous. And I need this to be equal to the value of f at 4. So let's check again the definition. It's a square root. If I plug in 4, I get out 2. So I have a 2 here on the right-hand side. And on the left-hand side, I once again use the limit of the definition that I have in the middle. So it's ax plus b. So the limit of x going to 4 from ax plus b is just 4a plus b. And this is my second equation from my linear system of equations.
Now that I see it, you had a linear function in the middle, but could also have been maybe another polynomial.
Yeah.
So then you would have more coefficients, but it would still be linear equations, still a system of linear equations where you can find a set of solutions.
Yes. So the linearity does not come from the fact that it's a linear function. It comes from the fact that the parameters that I'm plugging in are just there with a power of 1. The parameter, it's linear in the parameters. So I could also just use a linear combination of 2 different functions. But in this case, I think it's very nice to draw if it's also a linear function, but it's a good call.
No, the linear function makes it unique, the solution, because if you think of any polynomial in between, and you see the system of linear equations and you have more unknowns than equations, you might already know, I find more solutions.
Yeah.
So it's good to have a unique solution here. But because we said this is typical exercise, typical problem, you can just change it a little bit and you have a new problem. Therefore, I guess that makes it so popular. You can just make your own problem very quickly. And and that's why you need to practice it and really understand what you're doing. So if the problem changes a little bit, you say, okay, it's basically the same. I just work through these steps. So the next step that we are at is the linear algebra step. So we have a system of linear equations, and I just write it in this classical form of, we could just write it as a vector matrix multiplication. Should we do it like that? Yes, please. Reminds me that I have a whole course about linear algebra, which is still not finished, but a lot of videos will come, so it will be finished soon. And there we learn how to solve a system of linear equations in general, which is a thing you always need. You see, we do real analysis problems and you need linear algebra. So it's very important to learn linear algebra, no matter what you do.
Yeah, it's just a basic tool that comes up every one and then you really need to be sure that this is not the problem that you struggle with. So let's put in the numbers here. So the first equation is minus 2a plus b equals 12. So written in this matrix form, it's a minus 2 here, a 1 here, and a 12 there. And for the second equation, we have 4a plus b. So a 4 here, a 1 there. And then on the right-hand side, we have a 2 in here. So that's the system that we are going to solve. And if you recall, our original problem was for which parameters a and b function f becomes continuous. Well, they are basically right here. We just need to solve the system now. So let's solve the system
now.
Yes.
Okay, then show your linear algebra skills.
Okay, so first of all, what I do is I would not rewrite it in this form. If I'm short in time, like in an exam, I would just do it in this reduced form, which just consists of the numbers that I want to calculate with. So we basically get rid of this a times b vector.
Yeah, I would say you always should do that. When I first saw that, I thought this is just strange, but it makes so much sense. Yeah, you just concentrate on the essential part you need, and these are just the numbers, not the names of the coefficients or the names of the unknowns. They already are ordered. Yeah, you don't need the names, so you get rid of all the unnecessary stuff, and then you can calculate. So even if you calculate with a computer, it's still good to write it down like that you know what you have to put in. Yeah, so I like this reduced form now, so it makes sense. And I would say calculate with that always.
Yeah, so it saves some time, it saves space, and if you know what you're doing, it will give you the result.
If you don't make mistakes, it gives you the correct result. Yeah. And okay, maybe that's also a point. Yeah, you don't make maybe you don't make mistakes if you concentrate on the essential parts, because there's nothing that gives you some wrong ideas in this sense. You just concentrate on the numbers and calculate with the numbers.
So should we just solve the system? It's a 2x2 system, so this should go quite fast.
Yes.
So I eliminate this 4 here by adding 2 times the first row to it, and I get then a system in in a diagonal form, or upper triangle form.
Upper triangle form,
Yeah. So the first row stays the same. I don't change anything at all here. So then I get a 2 here, I get a 3 here, and a 26 here.
26.
All right. Yeah, because I'm adding 24 to 2.
No, I'm just fascinated how nice you chose the numbers in this problem.
So that's also the thing. So if you know what you're doing, you can be confident that these numbers are still right, even if they do not look nice. We'll see. So now we can solve this equation. So the last one reads 3b equals 26. So if we solve it for b, we see that b is 26 over 3. Not a nice number, but a fraction that we can work with, and that is already fully reduced. And now we plug this result back into our first equation, so which reads minus 2a plus b, so b is 26 over 3, equals 12. Yeah, so if we solve for a, we use we subtract the 26 over 3 from 12 and divide it by minus 2. And so now we need to do some basic calculations. If I would have chosen the numbers nicer, then you would get a nicer result. But so that's how it is. So the common denominator here would be 3. So we have 36 over 3 minus 26 over 3 divided by minus 2. So this gives us 10 over minus 6.
Mm-hmm.
And this is the result for A then. So
okay, we have B
let's
and
see.
A. Also, this is minus 5 over 3. So you have...
Yeah.
Yeah.
So we can also reduce this. Good point. Let's do it.
No, you don't have to do it. It's good that we have the unique solution now with the coefficient for A and coefficient for B.
Yes.
Very nice.
So the question asked us about finding A and B, and here are their values. And the problem is solved. So we now know if we set A equals to minus 5 over 3, so using a negative slope, and also point that is in here, so it makes sense. So our sketch was more or less accurate.
Nice.
And so that's about problem number 2.
I like the problem, yeah. It's a common problem. It's not too complicated. It's a lot of calculations, but yeah, you still check if you know the definitions. Like you have to state that you know the continuity at all the other points, and then you consider these jump points. So common problem, not too complicated, a simple problem. But still definitions of continuity go in. And of course, it's always nice to have some linear algebra in the end, which is not really needed because it's just 2 times 2. Yeah, linear algebra starts if it's more complicated, because 2 times 2 you can always solve, no matter how you do it. But it's easier to put it always into the common form and do the Gaussian elimination. And Fabian showed us how it works, and then the numbers are not nice, but you solved it. Yeah, very good. I don't see questions about this exercise. Yeah, there are no hidden videos. It's just the same. So don't worry. I put everything on the channel, which we do here. So this is the second live stream we do. So we are still figuring out if this works. But at the moment, yeah, it works. At least we can calculate stuff. Okay, Fabian, you can scroll down to my problem there.
Yes.
So now this is my problem, which I will solve now. I just have to change the screen. So nice, everything works here. Okay, but the same still holds from the beginning. If you have questions, just ask in the chat. No matter which questions, we will consider them. Like the question if there are some hidden videos. No, there are no hidden videos. You see the whole live stream on the channel. I just uploaded it afterwards. So if you can't participate here, you can leave and watch later. No problem at all. So now, this gets a little bit more abstract than the 2 problems before, because 2 problems before had explicit concrete functions. My first problem was one strange function, but still not so complicated. And Fabian's function was piecewisely defined with some polynomials and a square root, but very concrete. So we could calculate with concrete numbers. Here, that's not possible. This is more like a proof exercise, because you have an abstract function f. Yeah? The only property that we know of the function is that it is continuous. And continuous defined now on a compact interval. Compact, I choose it from 0 to 1. So it's the unit interval. But the point is, it's a bounded interval. Yeah, so, and closed. So we have a function defined from 0 to 1. And one important ingredient here is it maps into the same interval. So this just means the image lies also in I. Yeah, and I is our interval. Yeah, I can already tell you what we need is that we have a compact interval here. But the unit interval is just the simplest one, so I choose that. Does not change the proof or the exercise at all. So now, first problem here is we want to show that this function f, this continuous function, has a so-called fixed point. Yeah, when I say a fixed point, it does not have to be a unique fixed point. We just know existence of at least one. So fixed point. If you have never heard of that, not complicated at all, the definition is written here. It means the point is sent by the function to the same point. Yeah, fixed point. The point is fixed. The function does not change the point at all. Yeah, the function acts on points and sends them to other points in the same interval, but this fixed point is not changed at all. The function does not do anything. It stays at the same value. That's what we call a fixed point. Now, this is like a question in the chat before, like, how can you write proofs? Now, this is an example of a proof in some sense, so maybe that's already helpful. Now, Fabian, you know what a fixed point is? Did you hear about that before in your analysis classes?
Yes, so it comes up very often when one is trying to solve equations, or when one has a method and one wants this method to approach a certain point. So a fixed point is always a nice thing to have. And it's good that for continuous functions we know that in this precise setting that we have, apparently there's always a fixed point.
There's always at least one fixed point. Yeah.
At least one.
Yeah.
Yes.
It's a nice property which does not hold if you read part B, if you change this interval to the real number line. Yeah, so fixed points is special. G of x intersects f no matter what. That's a question in a chat or a statement. Goes into the right direction. I'm not quite sure. But yeah, maybe I take that and let's make a short graph here. Oh, maybe a straight line. So what do we need? We have the interval I. Let's say it's here on the x-axis, 0 to 1. We also have it here on the y-axis as well. So something we can remember now. We have a box. So if I draw a graph here, it's always inside this box. Yeah, because it cannot, it's only defined on this unit interval on the x-axis, and it should land inside the unit interval on the y-axis. So the whole graph lies inside this box. So there's another question. Would this property hold for any bounded interval? Not for any bounded, but for any compact interval. So closed and bounded. Yeah, so you can change I to an interval AB. Closed and bounded interval. Also interval is important. Yeah, so it needs to be connected. Yeah, so in general, I could have written AB here. It will not change the proof at all. And
it's maybe a good exercise to do afterwards to check whether this also holds for different
point.
Kinds of intervals. But I think it's really important to note that when doing these kinds of proof exercises or problems, every word, every definition, every aspect that you find in this exercise will matter at some point. You cannot just overread it and say, it's continuous. Doesn't matter.
Yeah.
No, it will be crucial.
Yeah, okay, but this is that's hard to say. Because we have designed the exercises, we are mathematicians, we get rid of the unnecessary stuff. Yeah, so therefore this is correct as you say it. Usually the problems work like this. But of course you could have stuff that's not needed for the proof, just because it's there. It's just we cleaned up the problem that it's not there, which makes it easier because you can use this fact. I need to use all the stuff that is there, but maybe it's not. So therefore, I'm not so sure if that is the correct approach to design exercise always like that, which we do. Yeah, so get rid of the unnecessary stuff. Because as you know, if you do some mathematical research, it's not that case. Yeah, you have to find out what is necessary, and afterwards you can get rid of that. Yeah, so maybe, but therefore I'm not so sure if you should always do this approach by solving problems like use all the stuff that is there, because maybe you don't need it. Or maybe you are smarter than the guy that designed the exercise and you see you don't need everything because you have a better idea. Yeah, you never know. Yeah, but we designed this exercise so we know, yeah, you need continuity here and you need that the interval is compact. Yeah, so. Okay, is there another question here? No. Then let's start with A. Show that f has a fixed point. Now, let's make a graph of f. Maybe f looks like that. Do you agree, Fabian? Could a graph of f look like that?
So the function does not have any jumps. So I say it could be a continuous function, and it also maps the unit interval to the unit interval. So it is not leaving this little square.
Yes, the box is not left at all. So it's a graph of f. So this could be f.
Yes.
So, but maybe I'll remove that again and show you the graph of the simple function of just f of x is equal to x, because this is what the fixed point says. Yeah, f of x tilde should be x tilde. So this could be the graph of the linear function f of x is equal to x.
Yeah, maybe you can scroll up a little bit that A is fully readable. Yeah.
You're completely right. Maybe we show the whole exercise. Okay, so now what do we have here? I draw the graph maybe in some blue color here. So we go from this corner to this corner. Yeah, so this is the upper corner. Now, this is the graph of the function that sends x to x. This is the linear function. It connects the two corners of this box. And now the function, the graph of the function f, and I made another one now, could be that. Graph of f. So Fabian, do you see the fixed point already?
I see, yeah, there is one fixed point which is at the intersection of the two functions that you
exactly
just drew.
there.
Yeah,
because that's the equation. There the equation is fulfilled. F of x is the blue line, or the dark blue line, and this lighter blue is the graph of this function on the right. So there the equation is correct, and that's our fixed point. So now the question is, can it happen that the graph of f does not intersect this line? And there you should already see, this is hard to fulfill because the function is continuous. So it has to be connected. So if you start here, the function cannot escape. Yeah, if it tries to stay on the one side of the line, it has to go into this point, and then we have the fixed point on the right. And the same on the lower part. So we have this intersection. It's needed. It's necessary to make the graph of f connected, to make a continuous function.
Yeah, so maybe you can also draw a quick example of a function that would have multiple fixed points, so that this x tilde would not be...
That's also a question in the chat. Can that happen? Yeah, of course that can happen, because this could definitely be a graph of f, and then you see a lot of intersections, a lot of fixed points. Simply because that's not what we prove. We don't prove uniqueness here, because it's not correct. But we prove the existence of at least one. So now that we are sure that we can prove it, let's try to do it. And I can already tell you, we will use the intermediate value theorem for continuous functions here, because that's exactly what guarantees that such a point exists. So now the question is, should we recall what it means? Maybe quickly. I'm not so sure if you... Maybe we do it. But first I want to show you the definition we need here. So I make some space. And then let's define. Let's define a function. And define the function g. Let's call it g. So I define g as something we can use, because this one is the equation of the fixed point. I put that down again. So this is the fixed point equation. We can put that to the other side, and then we have yeah, a question which is easier, I think, because now we ask for a 0 for a new function. And this function on the left should be my new function g. That's the idea. There is some remark in the chat that says f of x equal to x has infinitely many fixed points. Good point. Yeah, you can have infinitely many intersections as well. And that could be the same function, yeah. No problem at all, infinitely many. The number of intersections is odd? No. That's, I don't think this has to be odd. Or do I miss something? Maybe?
So I think if you consider the number of, if there's only a finite number.
If there's a finite number, yeah, okay. Maybe you can prove that as well.
Nah, you can draw like an arc that will have two fixed points, one at 0 and another one at 1. So
that's too easy. Yeah, let's do one example which is not odd. You can start here and then you can go to this point. Then you have exactly 2.
Yeah.
So yeah.
It's good that you ask these types of questions, because then you see it's really a general statement and it's hard to make to make some changes about it. So that's how you understand what the statement really does. And we need to work with a general function here and do a general proof. We cannot proceed by examples.
Indeed, but then, or in other words, we have to have all the examples in mind. Yes, and now we have another one. So, yeah, a lot can happen. Infinitely many fixed points can happen. No, it's okay. Your last comment about the parabola is exactly our example here. So, very good. Exactly like that, we could have an even number of fixed points. So now, new definition of a function. G of x defined in the same manner on the interval I. Interval I was the unit interval. So now this is the new function g. Question, is that a continuous function?
So f was given as a continuous function. X is also a continuous function, x mapping to x. So now we have a sum or a difference of continuous function. It stays a continuous function.
Stays a continuous function. That's something we prove immediate after introducing the definition of continuity, that combinations like addition, scalar multiplication, even quotients stay continuous. That's a simple combination here. It's just the difference of two functions that are continuous. The result is also a continuous function. Question from the chat, if we can't use the intermediate value theorem. Yes, we have to use it here, and we will do it now. I just want to define the function g, because we want to use it for the function g. And yeah, intermediate value theorem tells us that, and now I make a quick plot for the function g. Before I forget it, we discussed this is still continuous, sorry. So a continuous function g, also defined on the interval I. I make a plot for g, maybe not. Maybe a plot for a general function. Does not matter, could be g. So it starts somewhere, it goes somewhere, so, and then it ends here. And then the intermediate value theorem tells us that that all points here between the two values we have, and that are the values on the y-axis here, all the points there on the y-axis we hit. We hit all the points with x values. Yeah, so all the y values are hit with x values. That's the point we find an x for a given y value there. At least one. That's the intermediate value theorem. So maybe we say intermediate value theorem IVT. I hope you understand it with that. This is what we can use here. And then we have proven the existence of such a point. So now how do we do it for the function g? The function g, we can put in endpoint and a start point. The start point would be 0, the endpoint would be 1. So let's start with the 0. G of 0 is f of 0. Maybe I stay with blue here. F of 0 minus 0. Okay, we immediately know something about that, because f of 0 lies in our unit interval, and we subtract 0. So, in other words, this is f of 0, and this is at least 0. It's greater or equal than 0, and less or equal than 1. Yeah, but we know it's positive or 0. So, because it's the starting point of f. Will the range of g always be between -1 and 1? Because we subtract that, we could subtract more, yeah, should be. But it's not important for the range now, because we just write r anyway. Yeah, we know it's not I here in the image. Yeah, so the range of g is not so important right now. But of course, you can check what are the maximum values of f. What is the worst case that can happen in this difference? Then g of 1 is f of 1. Yeah, please recall this is the right hand side here, the value of g at the right hand side. This is f of 1 minus 1. Should I write it the other way? Maybe. Let's write minus 1 minus f of 1. Because then you see, okay, in the parentheses here, we subtract something from 1, but f of 1 can be at most 1. So we already know this lies in the unit interval, so it's less or equal than 1. So the whole thing in the parentheses is definitely positive or non-negative. This is greater or equal than 0, because we can't subtract more than 1 from 1 here. Or in other words, minus something which is positive or 0. So we have less or equal than 0 at the right hand side. The range of f, that's a question from the chat again. Range of f is known, or is not known. Yeah, it depends on the exactly the range. So it's okay. Yeah, the comment is correct. Like, you need to know the range of f to need to that you know the range of g, but at least you can give some bounds. That's the point. We know the bounds for the range of f, and therefore we also know the bounds for the range of g. Not so important, as I said. Important is now that we can apply the intermediate value theorem. And should I already say it? We want the 0. Yeah, we search for the 0 for giving the fixed point for f. So now we have it. We are greater than 0 or less than 0 on the one point and the other point. So 0 lies definitely inside these values we have. So the intermediate value theorem is applicable here to get a value for 0. So I call it IVT again and say, now we know there exists, maybe I'll write it, there exists at least one point, and we want to call it x tilde in I, also an important point, such that g of this x tilde is equal to 0. And that's it. We found a 0 for g, and a 0 for g is exactly a fixed point for f, because this one was f of x tilde minus x tilde, which means this x tilde fulfills our fixed point equation. And this gives the x tilde, and then with that, the proof is finished. So you can stop now. You just have to state the intermediate value theorem at the correct point. And we apply it to the function g. Therefore, it's necessary that it is a continuous function, because the intermediate value theorem holds for continuous functions. Okay, that's the proof for our problem A. I don't see questions in the chat, but maybe Fabian, you have a question for the proof here, or a comment?
So maybe a comment that is more general on these proofs that where you already know you want to use the intermediate value theorem. Sometimes there could also be a hint, like use the intermediate value theorem to show that.
Yeah, okay.
And then these proofs are always about finding the right function to apply this theorem to. And I think, yeah, in this case, once you have the function g, you see, all right, it's about finding zeros of g. So we need to find, well, points where we really know, okay, g will be less or equal than 0 and g will be greater or equal than 0, just like you did. And then, yeah, then you're there.
That's a good point. Yeah. So you need some idea. This definition of the function g was the idea we used here to apply the intermediate value theorem. Without this idea, it's hard because you need a function to apply it. The function f, yeah, you don't know because there was not a value you would find. Therefore, it is natural to do that. Yeah, to put it to 0 and then define a new function. So it's not like, yeah, this is you have to find this definition somewhere to use it. It comes out if you just subtract here. You immediately see, okay, I can state it as a question to find zeros. And to find zeros, intermediate value theorem also comes in mind. And Fabian, now we talk about part B, I guess. So we have proven that there's always a fixed point for the function f, which is defined on this compact interval, I. But if it's not a compact interval, like the whole real number line, this statement is not correct in general. In other words, part B now wants you to show a counterexample. Something that is not something that does not cross this line. So therefore, maybe we copy that. This is problem 4. So let's make more space here. Fabian, I realize we need a lot of space for solving our problems here today.
Yes.
Yeah. So what? I don't think it's a problem. We don't have a space problem here. We can always make more space. We also don't have a time problem. We just continue and continue solving problems here. Yeah. I also think if this channel reached the 100,000 subscribers, we can do a lot of calculations to celebrate that.
Sounds good, yeah.
Okay, so yeah, I hope this will happen then. Okay, part B. Now it changes. We don't have this boundary box. So maybe I completely delete it. And we just use the same line. So the same graph that shows us that there's a fixed point. So intersection points of the graph of f with this line gives us an intersection point. So, but now you see it's not a problem. You can use a function f that stays on the left the whole time. Yeah, there's no limit. You don't have to cross the line because you can always stay on the left. Yeah, that's the difference here. This boundary box was that pushes this function to the other function. And without this boundary box, it will not work anymore. So now, can we write down the graph of this function I sketched? Maybe not.
I think there's an easier way.
There's an easier way, yes.
Yeah.
There's definitely an easier way, and maybe you already see it. I can just use also a line. Yeah, so maybe f of x is equal to x plus 1 would fulfill it. Yeah, then you're always on the left, or always on the right if you want that. The real person. I think that's a comment, not for the problem. But yes, use the chat. At the moment, I think the chat is very nicely behaved. F of x plus 1, yeah, thanks. That's exactly the same, or almost the same, we have written down, so I think you meant that. So we just shifted by 1. So now we can prove that there's no fixed point. Should we do that?
I think it's a quick proof. So
it's a quick proof, so we do it. Okay. So assume there is a fixed point. Then it would mean f of x tilde is equal to x tilde. This is equivalent to, yeah, now I can write it. X tilde plus 1 is equal to x tilde by definition of a fixed point. Well, now we can subtract x tilde, which means this is equivalent to 1 is equal to 0. Everything fine. All the equivalences work. but this is a wrong statement in the real numbers. So a false statement is equivalent to the false statement. So this is a false statement, simply as that. Yeah, so there is no fixed point. It's not possible to fulfill this equation with this function. So the proof here is a counterexample where you just write down the proof for this example. Okay, any questions for this problem 2? I realize this is problem 2, Fabian. We are already in for more than 1 hour.
Yeah.
But it's okay. Yes, why not? It's exactly why we do that. We just calculate as we would calculate problems. Okay, I don't see questions. So let's go to the next problem. I put that problem in here because I wanted to talk about the Epsilon-delta definition. The next problem is, oh sorry, that was too much. The next problem is also about that, so we will talk about the Epsilon-delta definition now. And yeah, I put it in because I think sometimes it's just important to know how it works. It's not something you would use to prove that this function is continuous, maybe? I'm not so sure, I would not do it. I would more prove the simple examples and put it together. So, but now this exercise is formulated like, yeah, there's your function, explicitly use the Epsilon-delta definition to show that it is continuous. Okay, Epsilon-delta definition. I write it down as a definition very quickly, because there's a video about that. That's the reason I have the videos. You can just watch the video to see the whole definition. Here we solve exercises. And there's a question. Is that for me?
It's still about the fixed points.
Can we illustrate a function f having an infinite number of fixed points, which is always distinct from in any subinterval? Illustrate, yeah, I can illustrate that. If you want countable many, I can just do small oscillations that get smaller and smaller when you go to the top part. So you can illustrate that very easily, but I don't think I should go back now and do that. Yeah, you should do that on your paper. That's very good. So Epsilon-delta definition. I will be quick. F is continuous at yeah, maybe we put it at a point at x0 if and only if. So now it comes in. For all epsilon greater than 0, you find a delta such that for all x in our interval here, so okay, this is the interval 0 to 1, maybe I call it I again, that makes it shorter. So for all x in I, we have the property that if your input has a distance from x0 less than delta, this translates to the error, to the distance in the output, which means f of x minus f of x0 is less than our given epsilon. So this is the Epsilon-delta definition in a nutshell, very quickly with quantifiers. This is how you can remember it. Yeah, so for every epsilon you find a suitable delta such that you have this implication. Oh, there are more questions about the first example. Yes, yeah. I guess you can discuss that at. It looks good, as I can see it. Okay, now, if we want to show, maybe I leave it here. So if we want to show that f is continuous with this definition, it means for a given x0, we have to find and a given epsilon, sorry, we have to find the suitable delta. So therefore, if you write down the proof of this exercise or the solution, you would first say, okay, I fix epsilon and the point x0. So that's the first step I would do. Let x0 be in our interval I and epsilon an arbitrary small number epsilon. Epsilon should be an arbitrary small number. Yeah, small, it could be big, yeah, but of course you know how the definition works. It should be seen as a small number, but it needs to be positive. So now what is the perfect, suitable delta we can choose? Maybe we write it as choose delta now as a number. Choose delta as something that works. So, and now I can already tell you, we don't know what works if we don't try it out. So therefore, we leave this gap until the end. So I put the definition of the function here in the corner that we don't forget it. So this is our function for the day.
Yeah, that's always the thing about when you read through someone else's solutions, you see, he specified the delta right away, and you don't know where it comes from. You see where it comes from.
Yeah,
right?
if you read a book which is linearly written, it does not it's not possible otherwise. Yeah, you have to write it in a linear form. Yeah, you read from start to end. That's how a book works. It's always the case. Yeah, you see the proof, and there comes in a delta. A strange delta, you don't know where it comes from. You only know it after you read the whole proof, because the delta is designed such that it works in the end. It's not given at the beginning. But for the logic, for the argument, you have to give it at the beginning. Yeah, therefore, you still have to write it down like that you see the proof works. So that's the whole thing. Good that we don't work linearly here, Fabian. We can just fill in the gap later. And that's what we do now. So choose delta, and we will see how we choose it later. Then we can say that for all for all x in our interval. So maybe I use green color here. For all x in our interval, with the property, so with the property that x minus x0 is less than delta, whatever delta is. So we will see, but that's what we already can put down. We can calculate f of x minus f of x0. So this should be less than epsilon. Yeah, this is exactly what we want to prove. Yeah, this is what we put in. Implication says, okay, this should be less than epsilon. Okay. Backwards implications. The question about backwards implications, I don't understand it correctly.
So maybe it was because we left out the delta to be filled in the end, but it will be usual implications. So in the end, what we come up with will be a proof that you would read with the usual implications from top to bottom. So you won't have to read the proof bottom up.
That's the point. Yeah, this you can use your an extra paper to do some calculations before and then write down the proof. It's the implication should work in this direction. Yeah, so therefore, try to write it down in the normal logical way. And now you can calculate this difference here. So absolute value, and now we put in what we know. Yeah, we know the function f of x. I've written it in the gray box on the left hand side. So this would be x, 1 minus x minus, and now comes x0, 1 minus x0, absolute value. Okay, this is just the function f, and function f of x minus f of x0. So we can put that together a little bit. Maybe we write x minus x squared minus x0 minus x0 squared. Okay, I think this is all correct. And now we can pair it a little bit. So we can maybe we can put x0 here to the x, and maybe the other x squared. Oh, this x squared is plus, I guess. Now it's there again. Welcome back. We had a short break. Yeah, this can happen. So now I have written down this difference, f of x minus f of x0, and now we put it together because we want this x minus x0, because we already know it's less than delta. So therefore, my next step would be, just split it up into two things. So split it up into the first part and the second part. So triangle inequality of the absolute value. Yeah, Fabian, if you see some typos, mistakes I do on the way, please stop me immediately.
Yes, I do my best.
Thanks. That's already helpful. So yeah, the stream works. That's good. Okay, so this is less or equal than delta. No, this is exactly less than delta. Sorry, I was confused. We already know this is less than delta because that's what we put in our implication. And now we also want the other part to be less than delta something and put it together. So what can we do here? And this is a trick. Yeah, this is just how you can factorize that. So we can factorize it with minus and plus. Okay, yeah, maybe I should put the zeros both at the same spot. So there you can see that. Yeah, this is exactly factorizing that. Yeah, I'm always confused when some people call that a binomial formula. Yeah, but at least in Germany this is common to call this a binomial formula. But I would say it's not. It's just factorizing it. But I don't know how you see that, Fabian. I always find that confusing. And yeah. So now, no matter how we call it, we can factorize it, and then we can split it up into two absolute values. So the first one, maybe now I change the x0 again, because now we have it in the order we want. So I think that's correct. We also have this strict inequality if you want, because of this delta. So now, second part here. Second part is also less than delta. Yeah, because it's the same. The other one is not less than delta because there we have the plus sign. So now there we have to think. Maybe we can think, what is the worst case that can happen here? For at most, maybe I'll just write it down. At most 1 for x and x0. The worst case could be both are 1. That's the bound of this interval I. I think that's how we have chosen our interval. I can scroll up again. Yeah, this is defined on 0 to 1. So we can put that in here that we know this is at most 1. So the worst case would be this is 2, this absolute value. So in other words, this is always less or equal than 2. And then you see what we have is delta plus 2 delta. So this whole thing is less or equal, yeah, maybe less or equal is good enough now. Delta plus 2 deltas, so we have 3 deltas. And this one should be our epsilon, because that's what we want to prove. We want that this on the left is less than epsilon. So left hand side is less, and there's our less sign, than epsilon. Which means we can get that if we choose the correct delta. So now we have it. We can fill in the gap, choose delta small, smaller than epsilon, and exactly 1/3 of delta, of epsilon. Yeah, delta is 1/3 of epsilon. Then you can put in the delta at the last step here, and then epsilon comes out. That's the whole idea. Yeah, so we could calculate with the whole delta here, and then we see how small delta actually should be. Yeah, it should be 1/3 of epsilon, then it works. And that's all. Are you satisfied with that, Fabian?
Yes, so it works out quite nicely, and I think in the essence, well, what you did was, well, play with the definition of the function, plug in the delta that you already know for the difference, and then come up with an equation in the end that involves delta, a relation between epsilon and delta, such that we can solve for the delta that we really need.
You need this correct relation. Indeed, the correct relation is what we need. So therefore, you can try out a lot of things. This is not God-given. This is not the only solution. You can find other estimates that do it, because delta is not it's not fixed. Delta can be smaller than that, or even bigger if you find better estimates. But it doesn't matter. The point of the epsilon-delta definition is that you find a delta greater than 0. Doesn't matter what the value of delta is. At least you should find one that works. And now this definition works. Okay, and this works for all x0, by the way. x0 was fixed in interval, the whole proof works. So we have proven the continuity at all points x0 in the interval. So the exercise here is indeed finished now. We have talked about the epsilon-delta definition and applied it to the function f of x given with this definition here. So I don't see any questions in the chat. So I hope this is clear. This is also a standard exercise if you want to prove if you want to practice some epsilon-delta definition. I'm not so sure if this is a common thing. It's just to practice a little bit with epsilon and deltas. Can you show an estimation for delta if the interval I is not bounded? If the interval I is not bounded, we still could do something like that, but then it would depend on x0. Yeah, so here the worst case would be that you have x0 as a bound. It's okay. You can choose delta depending on x0 if we just talk about continuity and not uniform continuity. And then you have the same bound essentially. You know that the worst case would be that x is delta bigger than x0. So you also find a bound there. It looks a little bit more complicated, but you just can also write down an estimate depending on delta, and then okay, you have delta squared involved, and then you have to choose your epsilon with a square root, something that works. I don't write that down because if you want to make it beautiful, you have to think a little bit. But it will work exactly the same way. Just that your delta is then dependent on x0 if the interval is not bounded, in this case. So then there's another question. If I want to show that f is continuous if the interval is minus infinity to infinity. Continuity is a pointwise property, so it does not matter in this case. In this case we could use that, indeed, that we have a bound, but it's a pointwise property anyway. So you can choose it for you can show it for any point x0. So there are a lot of questions, but maybe I read them later. And now I give it back to Fabian, because Fabian also has a nice exercise, a nice problem about the epsilon-delta definition.
Yes, so I think we will continue more or less where we left off with the epsilon-delta definition, but we take it to a more abstract level. So we will once again be talking about a general function f that is now defined on the whole real axis, and we say it's continuous in one point x0. And so now we have an interesting statement, namely that if this function is strictly greater than 0 at this point of continuity x0, then the epsilon-delta definition will give us a delta neighborhood, so to say, of this point x0, where the function still is greater than 0. So I think this captures in some sense also the essence of continuous functions, that they do not change abruptly, or they don't jump. So they do not change too drastically from one point to another, as long as I stay close to this one point where I know the function. Let me do a sketch of the situation as well, because this will be helpful for the proof then. So let's say we are here on our real axis and we have a function f. And let's say this function f looks it looks something like this. And now okay, this function is continuous maybe everywhere on R, but what we know concretely is it is continuous at this point here, x0. So it is continuous here. And if we check also the function value, f of x0 is here, the function is strictly greater than 0 at this position x0. So you can see already from my drawing here that so I could also extend the region around x0 if I would do it that way.
Oh, you could extend it even more than that.
I could extend it even more. So the function hits 0 here. So let's make it a little bit more extreme here, because yeah, that's how this function will work. So I could choose a very large symmetric neighborhood here around my x0, and then we would see, okay, the function values of this very large neighborhood of x0, so all positions x that are to be found here, they will still map to positions to function values that are strictly greater than 0. So okay, this was once again one example of a continuous function that has this property. So, but we do not want to work with an example. We want to do something more, we want to prove something more general here, but I still think that this graph will help us to work out the solution to this problem. Because so if you recall the epsilon-delta definition that we had before, this definition works the other way around. We don't look in the neighborhood of x0 and then guess how large we should make this neighborhood. No, it's the other way around. So we first specify some neighborhood around f of x0. Let's say this is an epsilon neighborhood. And with neighborhood, I always mean it's an interval that contains this point and then goes epsilon up and epsilon down. So we have some certain cushion region here between the bounds of this interval. So this red interval here that I have is f of x0 minus epsilon and f of x0 plus epsilon. So I have just this open interval. It has f of x0 in the middle. And now the epsilon-delta criterion tells me, okay, given this epsilon, then there is also some delta. So I make this now in green here, such that whenever I take a function value out of this green neighborhood here, so so this neighborhood is too large, but because it once again needs to be symmetric around x0. So
yeah, you can make it smaller than if it's
we can do it. We can make it smaller. So that then I use another color. So there is this delta neighborhood. So this is now delta, and this purple interval here is x0 minus delta, x0 plus delta. Then the image of this, then the interval of the image of this purple interval will still be inside of this red interval. So I'll try to find the points that I need to map here. So the image, so it will be inside this red interval by the epsilon-delta definition. So to sum up, the epsilon-delta definition needs an epsilon from me, and it gives me back a delta that works for the neighborhood of x0. So now back to our original problem. So we now want to specify a region around this point of continuity, x0, where the function values are still greater than 0. And so I think it's a good idea if I enlarge this graph a little bit, because I want to I
Yes,
want to.
you have enough space here. You can make
Yes.
it as big as you want.
Yes, I want to show you the idea that is already hidden in this plot, and it's to be found in this point here. Because you see, if I don't choose the epsilon large enough, I choose a small epsilon, then this interval here won't contain 0. Yeah, in particular, all the function values that are inside this red interval are strictly greater than 0.
So that's already the idea of the whole proof, I guess.
So one could say that's the proof already. Yeah. So now we just need to write down the correct value of epsilon here, and we're done. So let's do it.
Or in other words, your epsilon just have to be small. Your epsilon has to be small enough that it works.
Yes.
And you can always make it smaller if it's too big.
Yes. So a good thing to do is, well, just reduce f of x0 by the half of its absolute value, or the half of its value. Then we will still get we still get a number that is greater than 0. Yeah, so we choose epsilon to be f of x0 over 2. So this is, of course, still greater than 0. So the Epsilon-delta criterion definition always needs an epsilon that is greater than 0. F of x0 is greater than 0, so epsilon will be greater than 0. So then the Epsilon-delta definition.
Maybe to emphasize again,
yeah,
what we put in is a continuous function. Yeah, this whole statement only works for a continuous function.
Yes.
And that's the property of a continuous function, you can say, and very important property.
Yeah. So we have a continuous function, and therefore we know it also fulfills the epsilon-delta definition. So plugging in this epsilon, the epsilon-delta definition gives us a delta that will depend on epsilon. It will also depend on our point x0 that we plug in, because, well, it's continuous at this point. So the delta will also depend on this point.
Yeah, it's common to write it like you do, like it depends on epsilon x0. Yeah. I try to avoid to write it like that, simply because it looks like you define a whole function, delta, of 2 variables, which we don't do. You just want to emphasize that there are dependencies involved.
Yes.
But you don't want to define a whole function for all possible values. So just to keep in mind, yeah. So if you see this in such epsilon-delta definitions, it does not matter, and it does not mean that there's a function involved. It just tells you in some short notations that there are dependencies.
Yeah. All right.
And yeah, maybe I should say it again. These dependencies are already given in the order of the quantifiers I showed you before. Yeah, the quantifiers were before the delta. So there was the I didn't write down the quantifier with x0, but you saw it in the definition. You have x0, and for every x0 we can choose and for every delta. I'm confused again. For every x0 and for every epsilon, you can choose a delta. So these are the dependencies here.
Yeah.
Delta depends.
So for every epsilon and for every x0, we get a delta.
Indeed. Okay, very good. So, sorry, I didn't want to interrupt your nice solution here.
Don't worry. So it's always good to keep on repeating the definition over and over again until you master it, and then
indeed,
naturally. So
maybe we can say that if you see the definition the first time, you shouldn't understand it. It's just too convoluted in this sense. But if you see it in applications and how we do it here in exercises, then it gets clearer and clearer.
Yes. So now let's complete the definition here, because then this will already give us, I think, the proof of what we are looking for. Because we now have a delta such that the following holds. Whenever I take a value x out of the interval of x0 minus delta and x0 plus delta, then I will also get that the function value f of x will be an element of the interval f of x0 minus epsilon and f of x0 plus epsilon. And so you wrote the epsilon delta definition down differently, right? So you used a difference of values and the absolute value in between.
Yes, we measured the distance. Yeah.
Yeah. So you just wrote the left side as x minus x0 less than delta, and the right hand side as f of x minus f of x0, or the other way around, smaller than epsilon.
Exactly, yeah. And
but
now you should see it's the same thing. Yeah.
And it's also a way of looking at the problem from a different angle. Yeah. So sometimes you want to calculate distances, and sometimes you want to visualize intervals.
Neighborhoods, in this sense. Neighborhoods of the points, yeah.
Yeah. So, and you can choose whichever you think works better. And I chose this one because I thought it will work better for this proof, because now what we need to show is, if I scroll up again to the question, so we have already found a delta, or a candidate for a good delta. We now need to show that f of x0 is greater than 0 for all x of this neighborhood. And I have already given a neighborhood. So I will just check whether the inequality also holds for this x. So take x out of this neighborhood. So, and now I need to check.
The first symbol is also a delta, x0 minus delta. Yeah.
So we take an x out of this interval here. I also give it a color, so you can match it to what I wrote down before.
Nice.
So I take out an x of this interval, and now I need to show that, or I want to check that f of x is actually greater than 0. This is what I want to show. So let me move that to the right, because what I already know is that f of x, just by the epsilon delta definition, f of x is an element of this interval here. So this means if I look at the left end of this interval, then I know that f of x will be greater than f of x0 minus epsilon. Now, this is just basic ordering of real numbers and how an interval works. Yeah,
you subtract.
It's just it's smaller than f of x. Yeah. So, and now what I plug in the last step is the definition of epsilon. So epsilon was f of x over 2, f of x0 over 2. So I have I copy the f of x0, and then I subtract the value of epsilon, f of x0, over 2, and then I need some more space on the right. So there is still plenty left.
I told you, you have as much space and time as you want.
Yes, good thing. Well, okay, now I'm just basically subtracting 1/2 from 1, which is 1/2. And then I have f of x0 over 2, which is greater than 0.
Mm-hmm.
Now looking at what we have just showed, f of x is strictly greater than 0 for all x of a delta neighborhood of x0. And this is just what we wanted to show in the first place. Yeah, so if I have a function that is continuous at a certain point, and at a certain point it's greater than 0, there is a neighborhood around this point where the function values still stay above the real axis. So some other visual way to think about this. And I think this is a really helpful fact that I recall a lot of times when doing proofs of continuous functions is, okay, it's greater than 0, So it will stay greater than 0 in a small neighborhood around this point.
Maybe you can
a continuous function.
You can visualize it like that. You have a continuous function. It has a point that is positive, a positive value, and then you can just zoom in into the graph.
Yeah.
You zoom in such that all you see are positive values. So you forget about everything else that might be negative, and then you see, if you zoom in enough, you just have a positive function. Yeah, and that's what happens here. You know, there are a lot of positive values in the neighborhood. Something you can use in other proofs. It's a property of a continuous function. And yeah, you can say the same for negative values, of course. Yeah, so you can flip it, and then they have the other property on the other side of the x-axis.
So that's the proof. And so I'm looking at the chat. Someone wants to ask a question of linear algebra problems.
Yes, our linear algebra problem stream will come soon, I guess. Yeah, so we marked this question. We take that with us. But this is our real analysis stream, and therefore maybe we keep the questions to the real analysis questions.
Yeah. So we also have a nice comment on the intuition of numbers greater than 0, or distance between 0 and a positive value. Yeah, you can always take half of it and it will stay strictly greater than 0, which is what we did here. But if you go through the proof, you will see, well, halving is fine, but taking every ration of it would also be fine, as long as it is between 0 and 1. Yeah, 1/3 would have worked the same way here.
It's just nicer, the calculation, because you subtract one half from 1.
Yes. Yes.
It's nicely symmetric. Yeah, everything works. At least you have to be less than 1. Nice. Every fraction works. But as you can see it like that, yeah. If you just take some portion of this value, you get you stay inside this positive realm.
Yes.
Nice.
So
hello.
Should we take a look at the next problem?
I was thinking about the next problems we have, and I'm not so sure how long your problem is. My problem is very quick. So
yeah, so I also brought a short one that involves a new definition.
Okay.
So
okay. Then
I think it's a great way to go on.
To end our problems
Yes.
here. Yeah, okay. Then let's do it. We advertise these, so so we should do it. I change to my screen again. So there we go. I always have to check if it worked. Looks good. Do you see your problem again? Yeah. So Fabian solved problem 5. By the way, all the problems are in the description. There's a PDF version of that. So usually you find them before the stream, so you can already solve them and then come with questions here if you want. Otherwise, you can just watch the stream for all the solutions. To be honest, I didn't write the whole exercise here. I kept it short because this goes to sequences of functions. So I didn't want to write the whole thing because I can explain what it is. So you have a sequence of functions here given by an index n. So for each natural number n, you have a function. And now the question is, are these functions continuous? And then the question is, okay, what about the pointwise limit? If you go n to infinity pointwisely, is this function also continuous? So as I said, this is a very quick problem. So maybe I just do it quickly. So a proof of that, or the solution of that, would be, okay, let's consider a natural number n fixed, which means we have our function fn given. So now, can we say this is continuous? Maybe I erase that and first talk about the parts. Yeah, this is very quick because we know, we can also go one step further. So x, the function that sends x to x. So maybe we write it down as a function. So x is the input and we put x to x. So this will be our function. This is the identity, the linear function, this is a continuous function. Easy to prove, the first thing we prove if we introduce continuity. If we have factors, the function stays continuous. Also something we have proven. If we take the absolute value, the function stays continuous. Also something we can easily prove. Now, if we add another continuous function, it stays continuous. So now we have 1 plus 1 is continuous, this one is continuous. Stays a continuous function. Now, reciprocals stay continuous if we don't divide by zeros, which will not happen here because we have a positive number anyway. So also this is a continuous function. And if we multiply with another continuous function, we are also continuous. So you see, this is just putting continuous function together. So the end result is, yes, this is continuous just by the properties of continuous functions.
Yes, and like it is said in the comments, so we are just recycling our knowledge about these building blocks of continuous functions, and then we just concatenate them, we multiply them, we divide them, and
they stay
good
continuous.
Thing is it doesn't change the continuity.
Yeah, so I can tell you, I have a video about these properties. These are easy to prove, either with the Epsilon-delta criterion or with the sequences. You can prove it by definition in general, and then you can use it all the time, that these compositions, these putting together with the basic operations we have, stays continuous. Prove that compositions of continuous functions are also continuous. Yeah, this is something you can prove in general, and which is not too hard to prove, which we will not do in such an exercise. You use these facts. Okay, continuous function. So now, for each n, n is fixed, then it's a continuous function. Now, the pointwise limit we can just calculate. So fnx, and then n to infinity. So maybe in order to do that, let's write it down. Should I write it down? Yeah, maybe. I put it into 2 cases. You can also do 3 cases. I'm not so sure if I should do it. Maybe, before I write it down like that, maybe we consider this as our sequence altogether. So now what do we have here? Maybe first thing is we can pull out the n. And we had a nice live stream about series 2 days ago, Fabian. We did a lot of calculations with these things. That was very nice. I hope we can do that again. Sorry, I want a straight line here. So, and then, if we do that again, we tell you, then you can join again. So I want to put this n divided by n out. So from the denominator and from the numerator here. And then we have 1 over n here left, plus the absolute value of x. So that's what I want to do here. So you see, this is correct. This is an equality which holds for every n. N is positive, so no problem here. And this is just 1, so we can cancel that. And now you can send n to infinity. And maybe now we do the 2 cases before I send n to infinity. Because this one is good if x is not 0. Because then you don't divide here with a 0, which is not a problem, but you see what it changed in the limit. It changes the limit in the sense this one holds for every x, which is not 0, but it's always 0 anyway if x is 0. Yeah, because the numerator is 0 in this case. So therefore, if you go with n to infinity, in the case that x is 0, it stays at 0 anyway. So we don't have to consider this case in this general form, because we already know it. So therefore, it's always good to take the simple case out, which makes this one much easier, because in the limit, this is x divided by the absolute value of x. Okay. So now if you see that, you can write down the limit, the pointwise limit. Pointwise limit. Should we give it a name?
So we could just call the function f.
Yes.
And then just calculate the limit at each point x.
F of x should be the pointwise limit for each point x, indeed. So now we know, because we already sent n to infinity, how the pointwise limit is split up into different cases. So now I can do the 3 cases I wanted. First, if x is negative. If x is negative, you see we have we have negative number divided by the absolute value of this negative number, which is the positive number. So we just have -1. Yeah, just the sign. We have 0 for vanishing x. So if x is equal to 0, the result is 0. And we have +1 if x is positive. So, as I said, this is a quick exercise because we don't have to prove anything now because we know this function. We know it's very continuous except for one point. And this point is the jump point here at 0. Yeah, that's what you should see. It's not continuous at 0. It's not a continuous function in the end. So that's the result here. Yeah, you have a sequence of continuous functions, no problem at all. But the pointwise limit gives you a result that is not continuous. So a general fact you can remember. Pointwise limits don't conserve the property continuity. This is a perfect counterexample for that. However, you know, uniform limits conserve it. So if you have a uniform limit, which we don't have here, by contraposition, yeah, uniform limits conserve the continuity. So, and that's all. Please remember, pointwise limits is very, very weak in this sense. It can destroy such a nice fact as continuity. Okay, that's the exercise here. Just very quickly recalling what a pointwise limit is and then calculating with some cases. I don't see questions in the chat. Maybe, Fabian, you have a remark?
So maybe one quick remark on the structure of how you solve this problem, because when looking at the function itself, one would maybe not guess that one would need a case distinction or to consider different cases on what would be happening. And this is something that comes up when we talk about pointwise limits, because, well, the limit may depend on the point x in our case, where we are calculating this limit. And, well, we have this absolute value that in itself contains a case distinction.
Yes.
So, yeah, and also this case of considering 0 or x not equal to 0, these are the things that one needs to keep in mind. So calculating pointwise limits always means calculating infinitely many limits at the same time, and then finding a right way to structure or decompose your problem into smaller parts where you know what is going to happen depending on the value of x.
Yeah, I agree with how you see it, that you have infinitely many points to consider. So yeah, keep that in mind. You can put some together, but not always. And here, taking x is equal to 0 out helps you. Because if you don't do that, you have to divide by x here, and then you have to go back again. Yeah, so it was good to take it out before, but of course, if you see it afterwards, you can just change it. So this question, so the last function is continuous. It's defined everywhere. So f of n is, so the original function with given n is continuous for every n, no matter which natural number n you choose. That was the result. But the pointwise limit function is not continuous. It's defined everywhere. That is not a problem. But you see it has a jump. So that's the result here. Because of this jump at 0, it's not a continuous function. Yeah, because of course it's continuous at 1 or at -1 or at -2. Yeah, but it's not continuous at the origin at x is equal to 0, and therefore the whole function is not a continuous function by definition. Okay, I think that's good enough for this problem. We are already online for 2 hours. Crazy. We're just calculating stuff straight for 2 hours. So we will finish up now. Fabian has a last problem, our problem 7 for today. And that's it for today. We will continue with other problems another day. But I think that's also a nice problem you have there. So this is about Lipschitz continuity. So maybe you can tell us about that first.
Yes, so as you may recall from also your real analysis course, there are different notions of continuity. Some of them are equivalent, like the one that we saw, epsilon-delta continuity and the continuity defined by sequences. So these are equivalent notions, but there are also stronger notions of continuity. One of them is uniform continuity, and another one that we are going to talk about next is Lipschitz continuity, which I find is a very fun definition of continuity, because it already comes with a nice and handy inequality in its definition. And I think it's a good way if we before we dive into the problem, we fix this definition. So, and the goal will be to show that Lipschitz continuity is stronger than continuity by doing the first step, which would be showing that every Lipschitz continuous function is also continuous. And we want to do this by using the epsilon-delta criterion. So what does it mean for a function f defined on the real numbers to be Lipschitz continuous? So, so the definition. So f is, and I just abbreviate this, so f is Lipschitz.
Can I interrupt?
Of course.
For the definition, you have f is defined on the real number line.
Yes.
Usually we have an interval for the domain of definition. I guess this also works. So you don't need the whole real number line as a domain for the definition.
Yes, so it will also work on subintervals. We can just stick with the real numbers for this problem, or should I change it?
Just to point it out again that the definition can be more general.
Of course, yeah. So so then let me be more precise. So it's Lipschitz on R.
Very good.
And then so if the following definition holds, so there exists a constant L. So this is a so-called Lipschitz constant that is should be greater or equal than 0 here.
So it's just a positive real number or 0.
Yeah. So such that for all points x and y in the real numbers, so if we were on an interval, then we would just take these points out of the interval. The inequality that I announced briefly will hold. This inequality takes into account the difference of function values, f of x and f of y, and says, well, this will be smaller than the Lipschitz constant times the difference of the arguments that I plug in. So we have a really nice relation between input and output in terms of differences for Lipschitz continuous functions here.
Maybe I should say here, y is also an input here.
Yes.
So it's not the output y, it's also an input on the x-axis.
Yeah. All right. So let's give this inequality a little star so that we can refer to it later. And the question that we want to answer is this function also, so does this already give us continuity by means of the epsilon-delta definition here? And also, I think something that we remarked earlier, that the epsilon-delta definition is a local definition. So we always take a point and say, well, the function is continuous in this point.
Yeah.
Now the question here tells us we want to show continuity on all of R. So we need to first start by taking a point x0 out of R and showing that the function is continuous in this arbitrary point x0.
True, you show it for all points, but maybe you can point that out here as well. This Lipschitz definition is not a local property because you say it's Lipschitz on a whole domain.
Yeah.
So and the definition also reads like that. Like you have for all points, you have this inequality, not just you fix one point and then you have something. Yeah, it holds for all points. So this is a uniform definition which is different from our usual continuity definition. So
it's a good observation. Yeah. So we now want to show continuity by the epsilon-delta definition in each point of on the real line. So we take x0 out of R, and we also take an arbitrary epsilon greater 0. So like before, this epsilon is just given. It's a number, no matter how big or how small. Important is it is greater than 0. So and now our goal will be to find a delta. So so for a delta that we need to specify again, so we don't need it. So we don't know it yet, but our proof will.
It's the same as before.
Yeah,
it
will be the same strategy as before. So so we have this implication that I just write down again for completeness here, namely that x0. So that for all x in a delta neighborhood. So let's say for all x in R, we have the implication that x0 minus x smaller than delta implies that f of x0 minus f of x is greater than epsilon. So
very nice.
Okay. If we have this, we have epsilon delta continuity in each x0, and as x0 was an arbitrary point, we get continuity on the whole real line. So how do we choose delta? Well, we just start calculating, and then hopefully this inequality will be handy here. So assume we have some delta greater 0, and we choose x and R fulfilling this inequality, x0 minus x smaller than delta. So let's look at the left-hand side of the implication that we need to show. So then f of x0 minus f of x. So this is the term that we need to estimate by epsilon. So, but if we now look at the definition of Lipschitz continuity, this is something that we can work with. Because, so the Lipschitz continuity now tells us that this difference of function values is less or equal than L, our Lipschitz constant, times the difference of the arguments, x0 and x. So now, once again, so think about the proof we had earlier on the epsilon delta definition. If we have a difference of x0 and x, we can estimate this one by delta. So this is less than L times delta. All right, and now we want this to be equal to epsilon for the whole proof to read, well, if I choose a delta in the right way, then I get for all x that are within a delta distance from x0, I get this estimate on the function values. And it should be clear now that from this part, we need to choose delta equals to epsilon by L. So, and this is also what I would write down here.
Very nice. But what do you do if the L is 0?
Okay, so that's a very good question. So we need to make a case distinction here. So let's do the first case, that L is strictly greater than 0. Okay? If in this case, we do the whole proof, and then this division here is all right. So what about the other case, where L equals 0? And this indeed will be a trivial case here. Let me copy down this definition for Lipschitz continuity.
Yeah, this question shouldn't make you a whole new case. Like, I mean, what
it's
does
a very
it mean?
short one. Yeah.
What does it mean if L is 0?
Yeah.
So if you look at the definition for the the Lipschitz continuity. If L is equal to 0, it's not so interesting anyway.
Yeah.
Or in other words, you can always choose a bigger constant anyway in the definition. So if L is 0, then replace it by L plus 1 and then use that in your proof. Yeah.
That you could do. The other thing I think that one also can see now from the second case here is that the Lipschitz continuous function that really has the Lipschitz constant 0 will be one that fulfills the inequality that for all x, y, and r, the function difference, the difference of function values will always be less or equal than 0. But as it's an absolute value, it's also always greater or equal than 0. So in this case, we can conclude that f is a constant function. And we know something about the constant function, namely that it's continuous.
True. Yeah, for constant functions, we don't have to prove anything.
Yeah. So that makes the second case also a very short one. And
yes, it's that's what I meant before. You don't need a second case because this constant is not fixed anyway, because you can always increase it. So it should not happen that you have 0. So, but of course, if you have 0, then you have more information about the function, which is also nice. Yeah, but your delta is chosen there. Maybe you can scroll up again, that we see the whole proof now. So your fixed delta is epsilon divided by L. And then everything works.
Yeah.
Nice. Okay. That's all. We have solved all our problems we prepared. So if there are no other questions in the chat, I would say we can wrap it up here. That was fun as always, just going through continuous problems. So very nice. I hope you enjoyed it, Fabian.
Yeah, it was fun. Nice amount of problems to cover. A lot of things to do with continuous functions. A lot of different exercise types to cover.
Indeed, and I like that we used a lot of epsilon and deltas, because people are usually afraid of epsilon and deltas when they talk about continuity.
Yeah.
But I hope you could see it's not magic at all. It's just, you have to put everything together and then, define the correct delta. That was something we learned today. So, can we show uniform continuity from here? Maybe uniform continuity is something we talk about next time. Now you know Lipschitz continuity, which is related. And thank you for coming. I hope you could enjoy it. The whole video will be up for, I think for forever. Let's see. So you can check all the solutions again if you want. And then I would say we do another session next time and solve more problems. Please use the comments to tell us which problems you want to see. This can be very helpful for us. Otherwise, Fabian, thank you for coming. I hope you come again.
Me. Yeah, looking forward to it.
It's much nicer to solve problems together.
Yeah, definitely.
Yeah, I'm also not so afraid to make mistakes if I know you check every step I do.
I'll do my best. Yeah.
Okay, then everyone, enjoy the day. Have a nice day.